Welcome to the deep dive. We're here to take on those really complex tech stacks, dense reports, piles of data, and, well, make sense of them for you. Today, we're looking beyond all the crypto headlines, the speculation, and getting into the bedrock technology, blockchain itself.
Yeah, our mission today is pretty straightforward. We want to cut through that hype, give you a solid fundamental grasp of what a blockchain actually is and, how its core mechanics work, what problems it genuinely solves, and maybe just as importantly, what its real limitations are. We're basing this on key sources, think technical standards from NIST, financial reports, that kind of thing.
Okay, let's start right at the core. What is it? Fundamentally, a blockchain is a digital ledger. It's decentralized, distributed.
Tamper evident and tamper resistant. That's key.
Right. And the NIST definition really emphasizes it's this shared record book spread out across lots of independent computers, which means, crucially, that you, as a user, can independently check and audit transactions. You don't need a central middleman.
And that phrase you just used, without relying on a central authority, that's really the breakthrough here. Before blockchain, making sure a digital unit of value wasn't spent twice, that double spending problem, it was basically impossible without a bank or some trusted go-between. By solving that, blockchain tech became what some of sources rightly call a fundamental value exchange protocol.
A value exchange protocol. That sounds foundational. Okay, so let's unpack the mechanics then. How does it actually maintain integrity across, a network where people might not trust each other? I know there are layers: infrastructure, networking, consensus, but maybe let's focus on the data structure first.
Yeah, let's zero in on the data and how it's changed. So at the data layer, you have information grouped into blocks. You can think of a block like a transparent digital box. It holds a batch of transactions that have been signed cryptographically and validated by the network.
Okay, transactions in a box.
Uh,
But what makes it a chain? How do they link up?
That's the clever part. Cryptographic linking. Every new block added has a unique header. And inside that header is a cryptographic hash, a unique digital fingerprint of the previous block's header. That's the connection.
Uh-huh. So each block points back to the one before it.
Exactly. And that link confirms the integrity of the block right before it. And that confirmation ripples all the way back, block by block, to the very first one ever created, the Genesis block.
Right, the Genesis block. So if I understand hashing correctly,
All right.
let's say a bad actor, tries to change a transaction from like 2 weeks ago. Just altering that one tiny piece of data would change the hash of that whole block's header, wouldn't it?
Precisely. It changes the fingerprint completely. And since every subsequent block's header includes the hash of the one before it, altering that one historical block breaks the chain from that point forward. All the following blocks would instantly fail validation checks across the network.
So any tampering becomes immediately obvious. That's the tamper-evident part.
Exactly. Tamper evident, which makes it highly tamper resistant. Because why bother trying if you'll be instantly caught and rejected by all the honest participants?
That is a really elegant security design. But okay, you've got this huge decentralized system running in real time. Things can't always be perfectly synchronized, right?
Yeah.
What happens if, say, two different network participants create and broadcast a valid block at almost the exact same moment?
Oh, that happens all the time, actually. It's quite normal. It creates what's called a temporary fork in the chain. Two competing versions of the next block, essentially.
A fork, so that the network disagrees for a moment.
For a moment, yes. The network then has to reach consensus on which chain is the true or canonical history. Usually that means picking the longest chain or sometimes the one with the highest score, depending on the consensus rules.
And what happens to the blocks on the shorter chain, the ones that weren't chosen?
Those become what we call orphan blocks. They were valid, but they just didn't make it into the main agreed-upon history.
Orphan blocks. Sounds a bit sad, like the transactions just disappear.
Not really, no. It's just a minor inefficiency, temporary. The transactions in those orphan blocks, they usually just get picked up and included in the next valid block that does get added to the main chain. They don't vanish. They just queue up again for validation. It shows the system works on eventual consistency, not instant perfection.
Okay, so the mechanics seem solid, relying on cryptography and consensus. But you mentioned trust earlier. The level of trust needed seems to really depend on the type of blockchain, right? Which brings us to this key difference: permissionless versus permissioned systems.
Absolutely. And that difference fundamentally changes the economics and the trust model. Let's take permissionless, first think public blockchains like Bitcoin or Ethereum. Anyone can read the ledger, anyone can send transactions, anyone can try to publish blocks. It's totally open.
Okay, open to all, but that means you don't know who else is participating. They could be anywhere, potentially malicious.
Exactly. Participants are often mutually distrusting. So, to secure the network against attacks in that environment, you need really robust and often very expensive consensus mechanisms, like proof of work.
That cost is the trade-off for operating in a trustless environment.
That's a good way to put it. Now, contrast that with a permissioned blockchain. Here, access is tightly controlled. It might be run by a single company, or maybe a consortium like a group of banks or supply chain partners who already know each other.
So there's some level of existing trust, or at least accountability, because you know who the players are.
Right. And because of that baseline trust, they don't need those super computationally heavy consensus models. They can use it much faster and cheaper. Maybe just a simple round-robin system where participants take turns publishing blocks. Much more efficient.
Okay, that makes sense. So let's dig into those consensus models, especially for the permissionless chains where they're so critical. The big one, historically, has been proof of work, PowerW. Why is it so intentionally expensive?
Well, proof of work forces participants, we call them miners, to spend huge amounts of computational power solving a really difficult arbitrary puzzle. Finding the solution is hard, but verifying it is easy for everyone else. The first one to find the solution gets to publish the next block and earns a reward, usually in cryptocurrency.
And the difficulty, the sheer energy cost, is the security feature.
Yes, it makes it incredibly expensive for any single entity to gain enough power to attack the network and rewrite the history. It's security through economic deterrence.
And this is where the numbers in the source materials just become staggering. The energy consumption. It's hard to get your head around.
It really is. The reports we looked at cited figures from, say, 2021, where Bitcoin alone was consuming around 121 terawatt hours per year.
121 terawatt hours? That's a lot.
It's enormous, more electricity than entire countries were using. Our sources specifically mention Argentina, the Netherlands.
Wow. Entire nations.
Yes. Highly developed nations, even. It prompted comments like the one from U.S. Treasury Secretary Janet Yellen, calling it an extremely inefficient way to conduct transactions. That reflects a deep concern about the sustainability.
Was there any kind of comparison to make that number, 121 terawatt hours, more relatable?
Well, think about the transaction throughput. You're using the energy budget of a medium-sized industrial country to process, relatively speaking, a very small number of transactions per second. The energy cost per transaction was astronomical.
Okay, that inefficiency and environmental concern clearly pushed the industry towards alternatives. And the main one seems to be proof of stake, POS. How does POS manage security without that massive energy burn?
It's a fundamentally different model. Instead of miners spending energy, you have validators who stake their own cryptocurrency. They lock it up as collateral.
So they put their own money on the line.
Essentially, yes. Their influence in choosing the next block is often proportional to the amount they've staked. But here's the catch. If they try to cheat the system, if they validate fraudulent transactions or try to attack the network, their staked assets can be automatically confiscated or slashed by the protocol. It creates a direct financial incentive to act honestly.
Right, so the security comes from the economic risk to the validators,
Yeah.
not from burning electricity.
Exactly. And that's why we saw that major shift you mentioned earlier. Ethereum, a huge player in the space, moved entirely from proof of work to proof of stake back in 2022, primarily to reduce its energy footprint.
Okay, so I have PowerW and POS as the main ways to secure these public chains. But even with these mechanisms, the sources seem to push back on the idea that blockchains are absolutely immutable. They use the term tamper-resistant. What's the difference?
That's a critical distinction, and yeah, it often gets lost in the hype. While changing blocks deep in the chain is practically impossible due to the accumulated work or stake securing them. The most recently added blocks, sometimes called the tail blocks, are inherently less secure. They haven't been buried under as many subsequent confirmations yet.
So they're more vulnerable.
They are vulnerable to being replaced. If another, slightly longer competing chain emerges, the network might adopt that one instead, orphaning the recent blocks on the shorter chain.
And this vulnerability is directly related to the infamous 51% attack, isn't it?
It is. The 51% attack describes a scenario where a single entity, or maybe a coordinated group, manages to gain control of more than half, 51% or more, of the network's block publishing resources.
So in proof of work, that would mean controlling over half the total computing power, the hash rate.
Correct. And in proof of stake, it means controlling over half of the total staked cryptocurrency.
And if they achieve that level of control, what can they actually do?
Well, they can essentially dictate the truth for new blocks being added. They could potentially prevent specific transactions from being confirmed. They could halt other miners or validators. And most damagingly, they could execute a double spend. They could spend some coins, wait for the transaction to confirm briefly, and then use their majority power to create a longer chain that doesn't include that spending transaction, effectively erasing it and allowing them to spend the same coins again.
That sounds catastrophic for trust in the ledger, so why doesn't it happen all the time?
For major blockchains like Bitcoin, the sheer economic cost of acquiring 51% of the hashing power is astronomical. You'd need billions of dollars in specialized hardware, massive amounts of electricity.
It's economically irrational, essentially.
For the big ones, yes, the cost of the attack likely outweighs any potential profit. However, and this is important, for smaller blockchains with much less hashing power or a lower total value staked, the 51% attack isn't just theoretical. It's a very real, practical, and potentially existential threat. We've seen it happen to smaller cryptocurrencies.
Yeah, that's a really important clarification on security. It's not absolute, it's economic and probabilistic, especially for smaller chains. Right, let's shift gears now. We've covered the mechanics and security trade-offs. Let's look at what people are actually building on top of this foundation, starting with the tech that really unlocked complex applications: smart contracts.
Smart contracts were a huge leap. Think of them as computer programs that live directly on the blockchain. They're designed to automatically execute the terms of an agreement when certain conditions are met. No need for lawyers, escrow agents, or other human intermediaries to enforce the deal. The code handles it. Ethereum really pioneered this capability around 2015.
So it turns the blockchain from just a ledger into something more like a decentralized world computer.
That's a great analogy. It can run code, execute logic, manage digital assets according to pre-agreed rules.
But wait, if these contracts run automatically based on conditions, how do they know about things happening outside the blockchain, like, say, the price of a stock, or if it rained yesterday for an insurance payout? Blockchains are supposed to be self-contained, right?
Excellent question. That's a fundamental challenge. Blockchains are deterministic, isolated systems. They can't just reach out and grab external data. That would break the consensus. This is where oracles come in. An oracle is like a trusted data feed that bridges the gap between the blockchain and the real world.
A trusted feed. Doesn't that reintroduce the very centralization and trust issues blockchain was supposed to solve?
It certainly can, and it's a critical point of potential vulnerability. If the oracle provides bad data, the smart contract will execute incorrectly based on that faulty information. That's why reliable oracle solutions are so important. The best ones often use decentralization themselves. They might aggregate data from many independent sources, use cryptographic proofs, have staking mechanisms to ensure honesty. It's a complex field in itself.
Okay, so oracles are a necessary, if potentially tricky, bridge. But even with reliable data, the whole idea of agreements being just code that must create headaches for existing legal systems.
Oh, absolutely. It's a major area of friction. How do traditional contract laws apply? What's the legal standing of a contract written purely in code? Who's liable if there's a bug in the code that causes losses?
If code is law, what court do you go to when the code misbehaves?
Exactly. These are really difficult questions regulators and legal systems are still grappling with globally. The legal status is often murky, to say the least.
And these smart contracts are the building blocks for a whole sector called decentralized finance, or DeFi, right?
Right.
Trying to rebuild finance without the traditional banks.
That's the core idea. DeFi aims to recreate financial services, lending, borrowing, trading, insurance, asset management, but on open, permissionless blockchain platforms using smart contracts.
What are some common examples we see in DeFi?
Well, you have decentralized lending platforms. Because users are often anonymous, these usually require over-collateralization. You might have to lock up, say, $150 worth of Ether to borrow $100 worth of a stablecoin.
So the risk for the lender is reduced because they hold more collateral than the loan value.
Precisely. You also have decentralized exchanges, or DEXs. These let users trade crypto assets directly with each other, peer-to-peer. They often use liquidity pools of assets supplied by other users, facilitated by smart contracts, instead of a central company holding everyone's funds and matching orders.
That sounds innovative, but I remember reading about a specific risk tied to DeFi's strength, its composability, the way different DeFi apps can plug into each other, like Lego bricks.
Yes, composability is DeFi's superpower and its potential Achilles heel. It allows for incredible innovation because developers can easily combine different existing DeFi services, money Legos, to create something new. But it also creates systemic risk. If one foundational DeFi protocol, one Lego brick, has a bug, gets exploited, or suffers some kind of failure, that failure can cascade rapidly through all the other protocols that depend on it. We've seen major incidents where a problem in one DeFi app caused huge losses across interconnected services. The Federal Reserve and other regulators have definitely flagged this interconnectedness risk.
Okay, so DeFi is a cutting edge, powerful, but also carries unique risks. Let's move beyond finance now and look at where blockchain is maybe delivering more concrete, less speculative value today, particularly in enterprise and supply chain.
Right, because for businesses to adopt this, it needs to solve a real problem and show clear ROI. And supply chain traceability is one of the standout areas. The Walmart example is probably the most cited one. They used blockchain for food traceability.
How much difference did it actually make?
A massive difference. The time it took them to trace the origin of a specific batch of mangoes, for instance, dropped from about 7 days down to 2.2 seconds.
7 days to 2.2 seconds. That's not just improvement, that's transformative.
Exactly. Think about managing food safety recalls, reducing spoilage. That kind of speed and transparency is incredibly valuable.
Wow. And it's not just food, right? I think the sources mentioned high-value goods, too.
Yes, the De Beers example with diamonds is another major one. They launched a platform called TrackOn. It tracks diamonds all the way from the mine through cutting and polishing to the retailer. It provides an immutable record to verify authenticity and ethical sourcing.
And the scale of that.
According to our sources, it was already monitoring something like 15% of global diamond production, over 600,000 individual diamonds registered on the platform. It tackles real issues of trust and provenance in a high-value industry.
So clear value in specific applications like traceability. Yet when we look at broader adoption across industries, the picture seems more mixed based on the reports.
It definitely has been. There's this interesting tension in the data. You had reports like Gartner's from 2018 saying only about 1% of CIOs reported any blockchain adoption in their organizations. It was still very much experimental territory for many.
Only 1%. That sounds tiny.
It does. But then in that same year, you had PwC surveying executives and finding that 84% claimed at least some level of involvement or exposure to blockchain technology. And PwC was projecting enormous potential future value, possibly exceeding $3 trillion annually by 2030.
So huge hype and potential recognized by executives, but very slow initial rollout by the IT departments actually implementing it.
That seems to be the story. There was excitement about the promise, but the practical hurdles, difficulty integrating with legacy systems, the lack of clear standards, regulatory uncertainty, the cost and complexity all slowed down actual deployment significantly.
Which brings us toward the end of our deep dive today. We've journeyed from the basic cryptographic hash linking blocks together all the way through consensus trade-offs, energy debates, smart contracts, DeFi risks, and now these real-world enterprise uses.
Yeah, it's quite a landscape. And if I had to synthesize one key takeaway for you, the learner, it's this. For blockchain to truly succeed and reach that massive potential value people talk about, it needs to pass a simple test. It can't just be a cool technology looking for a problem to solve, a hammer looking for a nail, as they say.
It needs a real use case.
A genuine business problem where it offers a significant measurable improvement over what exists today. Maybe a 30–40% improvement in efficiency or trust or cost reduction. That's the kind of benchmark some experts suggest. Because the core benefit, decentralization, it always comes at a cost, often in terms of efficiency, speed, or complexity. You only want to pay that cost when the benefit of decentralization is absolutely critical for your specific need.
That 30–40% improvement rule is a really useful filter. Okay, so for our final provocative thought for you to chew on, let's look ahead a bit, especially at the regulatory side, particularly in the U.S. It seems like efforts to just take traditional shares, like company stock, and put them on a blockchain tokenized equities are kind of stuck in regulatory limbo.
They are facing significant headwinds, yes, but there's been a potentially very important development regarding a different type of token. Utility tokens.
Utility tokens.
Specifically, tokens tied to what are called decentralized physical infrastructure networks, or DPINs. Think of networks where users are incentivized using tokens to contribute actual physical resources, like setting up wireless hotspots for a community network, or offering spare hard drive space for decentralized storage.
Okay, so the code can have a direct use within that network's operation.
Exactly. And the SEC recently issued guidance, or rather a no-action letter in one key case, that seemed to differentiate these tokens from traditional securities.
On what grounds?
It seemed to hinge on the application of the Howey test, the standard test for whether something is an investment contract, a security. The argument appeared to be that the success and value of the DePIN network depended primarily on the collective actions and efforts of its users building out the physical infrastructure, rather than solely on the managerial or entrepreneurial efforts of the initial founding team, which is a key prong of the Howey test.
Interesting. So it's distinguishing between a token that coordinates decentralized work versus one that just represents passive investment in a centrally managed company.
It's a subtle but potentially profound distinction. It suggests a possible pathway for certain types of tokens, those closely tied to demonstrable utility and user participation, to avoid being classified as securities.
So the final thought for you, the listener, is this. If this regulatory trend continues, favoring utility tokens linked to real-world user actions over simply tokenizing existing securities, could this deepen model become the dominant way new decentralized infrastructure gets funded and built globally? Might we see a future where capital formation for networks relies more on user participation incentives than traditional equity?
It's definitely something to watch. Keep an eye on DPINs and the evolving regulatory view on utility tokens. It could signal the next major wave of practical blockchain adoption.